Good morning, ladies and gentlemen. It is my big pleasure to tell you some few words about our research and development about the production of Inconel 718 when the lattice structure inside are used, and of course the parts are produced by technology SLM, which is connected into the PBF technology. I am and my colleagues, we are from the University of West Bohemia in Pilsen, from the Faculty of Mechanical Engineering, and our faculty concentrated all our research and development into the research center, which name is Regional Technological Institute. We have, and Pilsen has a very strong industry history, because we have here the Škoda company heavy industry, not Škoda Auto, but it is a heavy industry. And of course, we are connected into these companies where our main strategy partners are Dosan Škoda Power, the producers of the systems for steam turbines. Next is the Škoda Transportation, producers of tram, trails, and so on. Other one is Škoda Machine Tools, producers of the biggest one of the machines for heavy industry. And the last one and very strategic partner for today is Škoda Nuclear Engineering, and they are focused into the nuclear energy in Czech and of course in the world. How I said, we are from the Regional Technological Institute. It is one of the 4th research center of our university, and we have here 6 different laboratories, and of course one of them is laboratory of additive manufacturing. Additive manufacturing, generally SLM technology, it's perfectly usable in few all these areas for their benefits. Like we could to save a lot of weight, we could to prepare a special shapes, we could to connect it a lot of parts together in one functional part, so we save a lot of time for other producers, controls, and so on. And of course, for it, we could to use topology optimization, so we could to create it a bionic structure, or we could to use a lattice structure, or we could to combine it. In this case, you could to see our products in area of the cutting tools we implement inside the lattice structure, and we to a little bit optimize, of course, the frequencies of the tools, and of course we save more than 60% of the weight of the big machine's head. Next area for where we implemented our techniques is area of tooling. Here you could to see the hot forming tools. By our technology SLM, we print a whole body where we implemented a special lattice structure which optimized the heat on the surface and so on. And on the top, we use a technology DED, where we deposited a special material which increased the tool life of these components. And for today, the main topics is the area of energy, which is cooperation with Dosan Škoda Power. We prepare here this complex segment for first stage of the turbine, and we implemented here a lattice structure. It could be easy way, but there are lots of limits of use of lattice structure, and in area of energy or in different area, you know that there is a high safety factor. So we must solve it very briefly, and I want to show you the limits or what are the critical for the modeling of these systems to be functional. The first what is necessary to know is the process. Because how you know when we print the sample only in Z direction, we can say it's easy because there are the main process which is infill, and this infill created a good homogeneity of the material. The first time is infill, and next is a contouring. The contour created a final size of the part, and it finalizing the surface, but it is in Z direction. When we start to angle the part, that is used at another processes, generally downskin, and overlap with infill process parameters, but it is a very dynamic process, this overlapping. When we focus on this area of the downskin, then the angle is bigger and bigger, and we go close to the platform. It's creating a lot of potential defects. Generally, we can say that the homogeneity of the printed materials is more than 99.9%. And these few percentages, the mistakes of the materials are concentrated generally in area where we use downskins and overlapping of the infill. Here are concentrated pores, lack of fusions, and with the angles very quickly increase the roughness of the bottom surface. So in area of fatigue life, it is a very problematic. What we could do, we could machine this outer surface, and we solve a lot of troubles. But it isn't not idea of additive manufacturing. We want to use the parts which is only print, and we could use it. So on our department, we're looking for another solution during the process, how to optimize and how to minimize the internal defects on the base of neutral networks and on the base of adaptive system, which could remelt the problematic area, because during our process, every time when the one layer is printed, the melt pools are remelted 2.5 printed layers before. So for the experiment, in this case of lattice structure, we prepare standard samples, but into the body, into the shell, we implemented 2 different or 3 different lattice structures, BCC and gyroid structure. And what we did, the internal hole, we finished in this area. We should call it like short system. And the second, we ended the internal hole little far from this area, only in a few millimeters. And what is the main point? We machine the external surface, and of course the internal surface with lattice structure, it is not possible to machine, or there are some few possibilities, but it is very difficult without the repeatability and so on. So this is our setup. We print it in that direction, but the lattice structures are angled, yeah. So this is why. We use M290 system. This is the first one. It's a more than 11 years old machine. On the second one, we have implemented institute monitoring system, so we could see what's happened inside the melting pool. And this machine, small machine, is generally used for our students. So the experimental is, we use the standard process parameters in this case, because we want to show if somebody bought the machine and start to print and use the standard process parameters without the optimization, what could be happened with the modeling. Heat treatment according to standard, and of course the testing. The tensile test, it seems good in normal processes, but if you check it, the tensile strength is in limits, but the elongation break is under the minimum values. What's good to see? That inside the materials will be some troubles like pores, overheating areas, residual stress, and so on. Now we are going into the fatigue life. We tested this material, of course, in room temperature, but of course, we tested generally in area of use. It's in temperature 650 degrees. And here you could see very big differences between the systems. If we check it, you could see the differences between the same systems of the gyroids use. You could see that the differences could be 20%. If we check it between all the systems, we could see that the differences could be more than 30%. It's too much for this area of use. And why? We compare it with standard data. Here you could see a standards from the normal samples which is machined. the fatigue life of course increase. So we can say that we are 2 times lower than the other systems. Here you could see when are not machined the materials, we are close to our results. But we have machined the outer system, outer surface, but internal surface is not machined. Now we are going to the fractures at this time, and here you could see a typical troubles in the materials. And here is a detail of the connection of the rods of the lattice structure. And here you could see that there are a lot of concentrated stick balls of the powder. Some balls are only stick, but some balls are little melted into the surface. And in this area, there are a good potentials for the cracks. When we check it a little deeper in this area, we could see that there are a lot of lack of fusion. There are holes where insides are the non-melted materials, and this is a big trouble in this area of fatigue because this is a nice concentrator of the cracks, of course. When we check it visually, we identify generally in whole samples in this case that the cracks are that the crack goes from the internal surface to outer surface because the outer surface was machined. So the domination of the cracks are really roughness, and the domination of the cracks are really the quality of the print. Now we are analyzing the trouble areas on the base of the process. We check the surface of the melting area, and in case of BCC structure, you could see that very quickly is changing the area for the melting. So it means that very quickly is change the thermal processes in this case. In case of BCC is little better. We can say it's close to constant. And this in case when this area is connected into the shell of the body, there are a lot of concentrators of potential defects. And generally, this is the trouble because the downskin in this area. When we check the process, here you could see that the rods are connected together. A lot of downskins are used. This is the nice potential for the internal defects, and this is why all the cracks are created in this area of the connection of the lattice structure. The next point is that in this case, on the bottom, we can say it's a 40 degree. It's a constant roughness about 15. But in this case of gyroid, the roughness is changeable on the base of the radius. Now, here you could see the simulation, and here you could see in the critical area of the connection of the rods together that really the simulation indicated the overheating area. So this is why there are big differences. And when we check the areas where the downskins are starts, because here is a Z direction, and here, in this case, start the process of the downskins and infill of the overlap. This is the point of the outer point. This is the start of the internal point. And here you could see that the long systems are different point than the shorter systems. So that means that in this area is totally all the negatives processes for the print. And if we check it, the areas of the short systems, there are the maximum of the concentrators of the cracks of the defects. When we check it, but not on this same part, but on different samples, here you could all the white points is the potential defects, and here in this area, when start the downskin, you could see that the amount of the potential defects increase on the base of the process. So this is a danger. This is a very interesting point, because it is necessary to know when we to do some design of the special parts, because on the basis of it we could to eliminate a lot of things, of the negative things, and we could to create it a repeatability and reliability system for our customer. So for the end, I just discussed with the organizer. I would like to invite you to Pilsen, because on the February we organize our big conferences. We have here more than 180 participants, and this symposium will be focused on additive manufacturing, from design to qualification, and for a sustainable advanced manufacturing system. So you are very, very welcome. And of course, in Pilsen, we have a football club. We have a Pilsner Urquell. I think a lot of you know it, but what is not so much know, we have here a sparkling wine, which is typical product for the Pilsen and our region. So thank you for your attention, and I'm open for your questions. Thank you.